Yo kids, so we're back on the 2016 Physics AS Unit 1 paper, question 6 out of 7. This was the projectiles question, a bit weird this year, gotta be honest. Starts off nice and easy. Here's a parabolic projectile path, symmetrical about maximum height. Describe and explain how the vertical and horizontal components change during the flight. And the key is here, ignore the effects of air resistance. Well, because we can ignore air resistance, the horizontal component of velocity will remain constant throughout. Right, that's 1 mark. And then, of course, because of gravity, vertical component will decrease on the way up to the top of the flight, and then it will increase on the way back down, and that's due to gravity. So that's a nice, easy 3 marks. Right, the second part of this question was a little weird. Our projectile is a space probe Philae dropped onto a comet 67P, and it bounced twice before coming to rest. Okay, so you can think of that as one parabolic projectile motion and the other one there. It said a newspaper used the following image to describe the landing. So you've got to look at it pretty carefully to get the information out here. In this first bounce, the hang time was 1 hour 50 minutes. Right, so that's the time of flight for that bounce there. It says on this first bounce, it travels about 1 kilometre up. So at maximum height, it's gone 1 kilometre. And an equal distance across the comet. So the range of flight is 1 kilometre. It tells us over here that the escape velocity, which comes up later, is 88 centimeters per second. So a change of units there. So I got hours, minutes, miles, kilometers, centimeters. They're really trying to catch you out on unit conversion, so be very careful with it. Use the information from the image to calculate the horizontal velocity. Right, it's only 1 mark, so it can't be difficult, and it isn't. The horizontal velocity is the horizontal distance divided by the time taken, right? So the horizontal distance to get from there to there, they've told us is 1 kilometre, 1,000 metres, and the time taken was 1 hour 50 minutes. So think of that as 110 minutes, and then multiply that by 60 to get it into seconds. So do the 1,000 divided by 110 times 60, and that'll give us a velocity in meters per second of 0.15. Right, not too difficult there. Excuse me. Right, second part. Considering the first bounce, so we're only talking about that first bounce that was 1 hour 50 and a kilometre across and a kilometre high, right? Show that the value, it's a show that, so they give us the answer, which is great. Show that the value of the acceleration due to gravity is approximately 0.0002. So much smaller than our 9.8 here on Earth, right? So let's write down what we know. We know that it's gone 1,000 meters to get to the top of the flight, right? And at the top of the flight, because it's a parabolic path, the time taken to get there is half of that 1 hour 50 minutes, which is 55 minutes, multiplied by 60 to get into seconds is 3,300 seconds. Now we're looking for acceleration. So we want to think of what suvat can we use here to get A. So there's a couple of options, right? But the best one is we know that at the top of that flight, if we are talking about the vertical component of velocity, it will be 0 for that instant. So you will have done this in class. So let's use S equals ut plus a half at squared. S is 1,000. That's the distance it's travelled to get to the top of that flight. Ut is 0. Because initially the velocity was 0, and at the top of the flight the velocity in the vertical component is 0. Half at squared. T we just worked out, 55 minutes times 60. So if I plug those numbers in the calculator, and it comes out as 0.00018, which is very close to the 0.0002 that it asks us to show. On to the next bit. Show that the vertical velocity immediately after the first bounce was greater than 60% of the escape velocity. Right, now it told us the escape velocity on the diagram was 88 centimeters per second. So do yourselves a favour and convert that into meters per second. So the escape velocity was 0.88 meters per second. Right, now, we know that for that first bounce, the initial velocity is 0. It bounces and it takes 55 minutes times 60 to get there. And the acceleration is 0.00018. We worked it out previously. If we didn't, we could have used this figure from the show me, right? So I'm going from the top of the flight, right? So if I sketch it, here's that first bounce. I'm going from this point here. So initially my vertical velocity is 0. That's the time it takes to get to the bottom. That's the acceleration it's experiencing, and we're finding the velocity at the end of that first bounce, which would then be immediately after the first bounce, right? Chuck that in the calculator and it comes out as 0.594 meters per second squared. Now they want us to show that that's greater than 60% of the escape velocity. So find 0.594 as a percent of 0.88. So divide that, multiply by 100. It comes out to 67%, which is obviously greater than 60. Happy days. And then the last one is one of these silly ones that they like to chuck in, right? We've had a few of them. Consider the following facts and discuss whether or not the mission was justified, right? For 3 marks. So it cost a lot of money over 10 years, £1 billion. 2,000 people were involved. We did develop some advanced solar cell tech. There was 28,000 retweets just in the first hour. And they did discover, imagine this, organic molecules on the comet surface. So they want to discuss whether or not the mission was justified. So this is subjective, obviously. So you can just write some fors and against and pick up the marks. So the obvious reasons for saying it was justified: it created a heck of a lot of jobs, 2,000 people. It was instrumental in developing new technology, the advanced solar cell. It had great publicity and generated great interest in science, 28,000 retweets. Things to say it wasn't justified: there was a risk of failure, and it would have been of huge financial cost. 1 billion. What if the rocket didn't even make it? It's had little actual impact on society. I don't know much about the advanced solar cell tech, and I certainly don't know anything about organic molecules being detected off this planet. And 1 billion, what a lot of money. Could have that been spent on something a little more pressing or useful to the human society? A rather unusual projectiles question, but essentially one that I'm pretty confident we can do. Right, 1 to go.